All right, so we continue chapter 5 by introducing the concept of strong mathematical induction in section 5.4. As you remember, in the previous sections, we introduced mathematical induction. Now, as an extension of mathematical induction, we introduce a strong mathematical induction. So let's first define the principle of strong mathematical induction. Let P of n be a property that is defined for integers n, okay? And let a and b be fixed integers such that a is less than or equal to b. Now suppose that we have the following two statements true. The first one, which is called the basis step, which is, you see, very similar to what we had for mathematical induction itself, basically says P of A plus 1, all the way to P of B are all true. And the second step, which is the inductive step, says for every integer k greater than or equal to b, if P of I is true for all integers I from A to k, then P of k plus 1 is true. So if you compare it with the ordinary mathematical induction that we defined before, the inductive hypothesis is different. In the ordinary mathematical induction, the inductive hypothesis was P of k is true. But here, the inductive hypothesis basically says P of A is true, P of A plus 1 is true, all the way to P of k. So the inductive hypothesis in the strong mathematical induction is much longer than what we have in the mathematical induction. In the strong mathematical induction, inductive hypothesis is P of I is true for all integers I from A to k. Okay, so after defining the basis step and inductive step, we can say if these two steps are all true, then we can say for every integer n greater than or equal to a, we can claim that P of n is true, and this claim is supported by strong mathematical induction. So sometimes instead of saying that P of I is true for all integers I from A to k, we can, state inductive hypothesis as P of A plus 1, P of A plus 2, all the way to P of k are all true. Okay, so this is another way of stating the inductive hypothesis for a strong mathematical induction. Okay, so as an example of strong mathematical induction, let's prove theorem 4.3.4 of the book, which basically says any integer greater than 1 is divisible by a prime number. And we are going to prove this theorem using strong mathematical induction. Okay, so the first step is to define P of n. What is P of n? P of n in this case is this sentence. N is divisible by a prime number. So in order to prove this, we have to first prove the basis step. In this case, A and B are both 2, so we're going to show only P of 2 is true for the basis step, and here is how we show it. We say P of 2 is divisible by a prime number, and since 2 is divisible by 2 and 2 is a prime number, so P of 2 is correct. So we are done with the proof of the basis step. Now let's prove the inductive step, which basically says show that for all integers k greater than or equal to 2, if p of I is true for all integers I from 2 to k, then p of k plus 1 is also true. Okay, so obviously, if you're asked to say what the inductive hypothesis is, you can say p of I is true for all integers I from 2 to k, or in other words, you can say I is divisible by a prime number for all integers I from 2 to k. That's called the inductive hypothesis. And given the inductive hypothesis, we are going to prove p of k plus 1, which basically means k plus 1 is divisible by a prime number. Okay, so in order to prove the inductive step, we use direct proof of proof by division into cases. We consider two different cases. In the first case, let's assume that k plus 1 is prime, and in the second case, obviously, let's assume that k plus 1 is not prime. Okay, so the proof of the first case is pretty easy, because if k plus 1 is prime, then obviously it's divisible by itself. So k plus 1 is divisible by a prime number, namely itself. So the case 1 of inductive step is taken care of. Now let's focus on the second case, which basically says k plus 1 is not prime. So in this case, since k plus 1 is not prime, so it's a composite number, so it can be written as the multiplication of two integers a and b, such that both a and b are not equal to 1. Okay, they are both between 1 and k plus 1 exclusive. So basically you can say a is between 2 and k inclusive, and b is also between 2 and k inclusive. So by inductive hypothesis, since we know that a is divisible by a prime number p, so since k plus 1 is equal to ab, k plus 1 is also divisible by a. So k plus 1 is divisible by a, and a is divisible by p. So based on the transitivity of divisibility, we can say that k plus 1 is also divisible by the same prime number that divides a. So basically, regardless of whether k plus 1 is prime or not, we have proved that it is divisible by a prime number. Okay, so as another example of strong induction, let's see example 5.4.2, which basically wants to prove a property of a sequence using a strong induction. So let S0, S1, S2 be the sequence that we are going to prove one of its property using a strong mathematical induction. And in this sequence, we know that the initial terms are S0 is 0, S1 is 4, and the other terms are defined recursively. Basically, we have S sub n is equal to 6s sub k minus 1 minus 5s sub k minus 2. Okay, this recursive equation is true for all integers k greater than or equal to 2. Now the property that we are going to prove for this sequence is that its general formula is s sub n equal to 5 power n minus 1. And so since we are going to prove this using a strong induction, in the first step we are going to define the property p of n formally. So p of n would be this formula, would be s sub n is equal to 5 to power n minus 1. Now we are going to start proving the basis step, which says P of 0 and P of 1 are true. So 0 is equal to A in the definition of a strong induction at the beginning of the section. If you remember, we said there are two fixed integers, A and B, in the definition of a strong induction. So 0 is the fixed integer A in this problem, and 1 is the second fixed integer B. So the basis the basis step basically wants us to prove that P of 0 and P of 1 are both true. So in order to prove that P of 0 and P of 1 are true, we must show that S of 0 is equal to 5 to the power 0 minus 1, and S of 1 is equal to 5 to the power 1 minus 1. So we have to replace n by 0 and n by 1 in the general formula that is given in this problem. So if you simplify the right hand side of these two equations, you see that S0 becomes 0 and S1 becomes 4, and that's what exactly we were given by the definition of sequence S. So the basis step is true, so the only thing that we are going to prove here is to prove the inductive step. So as you see, the inductive step is for all integers k greater than or equal to 1. If P of I is true for all integers I from 0 to k, then P of k plus 1 is also true. So the inductive hypothesis here is that for all integers k greater than 1, if you suppose S sub I is equal to 5 to the power I minus 1 for all integers I, where I is between 0 and k inclusively, then P of k plus 1 must be true. So inductive hypothesis becomes S sub I is equal to 5 to the power I minus 1 for all integers I from 0 to k. And assuming that inductive hypothesis is true, we must show that P of k plus 1 is true. It means that S sub k plus 1 is equal to 5 to the power k plus 1 minus 1. Okay, so in order to show that, we start from the left-hand side of the equation and we simplify it step by step to reach to the right-hand side. So here, as you see, S sub k plus 1 is equal to 6s sub k minus 5 s sub k minus 1 by the definition of sequence S. And then after that, we can simplify S sub k and S sub k minus 1 by replacing them with their equivalent values that we are given in the inductive hypothesis. So S sub k based on inductive hypothesis is equal to 5 to the power k minus 1, and S sub k minus 1 based on the inductive hypothesis is equal to 5 to the power k minus 1 minus 1. So by replacing S sub k and S sub k minus 1 with their equal values, we will get 6 times 5 to the power k minus 6 minus 5 to the power k plus 5. And using the law of exponents, we will get to the right hand side of the equation that you are going to prove, which is 5 to the power k plus 1 minus 1. And here we can claim that we have proved both the basis step and the inductive step of the strong induction, and as a result we can claim that we have proved the property of the sequence S, which is its general formula. Okay, so the last thing that we see in chapter 5 is section 5.6, which is about the definition of sequences using recursive equations. So basically a recursive relation for a sequence like this a0, a1, a2 all the way to infinity is a formula that relates each term like ak, a sub k to certain of its predecessors, ak minus 1, ak minus 2, all the way to ak minus I, where I is an integer such that k minus I is greater than or equal to 0, or I is an integer less than or equal to k. So the initial conditions for such a recursive relation specify the values of a0, a1, a2, all the way to ai minus 1, which are basically the first I initial terms of the sequence A. So here we see an example of the book, example 5.6.1, which basically tries to compute the terms of a recursively defined sequence. So let the sequence C, which starts from C0, C1, C2, all the way to infinity, be recursively defined in the following way. The recursive relation for C is C sub k is equal to C sub k minus 1 plus k times C sub k minus 2 plus 1. And the initial conditions are C sub 0 is 1 and C sub 1 is 2. Now the question is find C sub 2, C sub 3, and C sub 4. Okay, so the first thing that we need to do in order to calculate C sub 2 is to use the recursive relation for k equal to 2, and we will get this equation. We get C sub 2 is equal to C sub 1 plus 2 times C sub 0 plus 1. And if you replace C sub 1 and C sub 0 with their equivalent values given in the initial conditions, you will get 2 plus 2 times 1 plus 1, which basically add up to 5, so C sub 2 is 5. And since you have C sub 2, then you can calculate C sub 3 using the recursive relation. So C sub 3 is C sub 2 plus 3 C sub 1 plus 1, which is 5 plus 3 times 2 plus 1, because we replace C sub 2 with 5. And as a result, C sub 3 becomes 12. And the last one, which is C sub 4, is obtained using C sub 2 and C sub 3, because C sub 4, based on the recursive relation, is equal to C sub 3 plus 4 C sub 2 plus 1, which is equal to 12 plus 5, 4 times 5 plus 1, which adds up to 33. Okay, so now let's take a look at the example 5.6.4 of the book, which basically introduces the Catalan numbers, and it gives an explicit formula for the Catalan numbers. As you see, C sub n is equal to 1 over n plus 1 multiplied by 2n choose n. So here we are going to create a recursive formula for the same sequence, for the sequence of Catalan numbers, and basically we are going to prove that this recursive equation works for the Catalan numbers. The recursive equation is C sub k is equal to 4k minus 2 divided by k plus 1 times C sub k minus 1. So this equation basically relates any term of the Catalan numbers to its predecessor. For all integers k greater than or equal to 2. So in order to prove this recursive equation, I'm going to start from the right hand side of this equation, which is 4k minus 2 divided by k plus 1 times c sub k minus 1. And I'm going to simplify it and go further and further until I reach to the left hand side of the equation, which is c sub k. So in order to start simplifying the right hand side, I will use the explicit formula or general formula specified here to replace c sub k minus 1. So as you see, I write c sub k minus 1. I replace c sub k minus 1 with its equal value, which is 1 over k, and 2k minus 2 choose k minus 1. And as you see, I wrote the explicit formula of n choose r here, which is basically a quotient with the denominator of 2k minus 2 factorial and the denominator of k minus 1 factorial, k minus 1 factorial. Okay, so this giant product can be further simplified by factoring out a 2 from 4k minus 2 and write the 2 here and write the other half of that product, which is 2k minus 1 here, pretty close to 2k minus 2 factorials. And in the denominator also, I basically wrote k minus 1 and k minus 1 factorials close to each other, so that later I can simplify them into k factorials. Okay, and in the next step, I basically multiply k in the numerator and denominator of this quotient, this giant quotient, so that in the next step I can write 2k factorial in the denominator and 2k minus 1 factorials, 2k factorials in the denominator. So the final result is this, is 2k factorial over k factorial multiplied by 1 over k plus 1, which if you look at here, that's the general formula for the kth Catalan number. So we are done with the proof.